Yeah, recording.
All righty. Welcome, everyone. This is the second workshop for N2E Robotics. My name is Jack Lowry. Just a little bit of background on me. I'm an undergraduate for Rutgers studying electrical engineering and computer science. I've been doing robotics for a while, and specifically, you'll figure out that once you kind of start getting familiar with robotics, ROS is going to keep popping up back and over and over again. So this is a really good opportunity to kind of get a basis of an idea of what ROS is, and I'm going to kind of walk through all of the various parts of ROS because it's really big. It's a really big piece of software and a lot of different topics to understand and why we tend to use it so much. I recommend everyone here, like, if you have any questions, please feel free to stop me. I'm probably just going to be talking for a while, so just send your questions in the chat or even just speak up. I'd be glad to answer any questions anyone has. Okay, so before we talk about ROS in specific, we should talk about kind of what was the landscape before ROS was invented, right? So in general, there was just a lack of standards for code on robots, right? Code wasn't reusable. Every time your lab or people gave you a new robot, you'd have to code a lot of things from scratch, even common algorithms, just because they were so specific to that robot, right? I mean, if you're depending on telling a very specific motor to move in a very specific way for your algorithm, obviously when you transport that to the next robot, it's just not going to work. And I bet it made a lot of people feel like this guy kicking the robot. That's what they wanted to do. And that's kind of why it was invented. That's kind of the reason it exists in the first place. So then ROS was born, right? So ROS stands for Robot Operating System. It's an open source set of software libraries and tools that help you build software applications that work across every robotics platform that exists, right? Now, this doesn't mean you make one piece of software and it runs on one specific robot. It means you make one piece of software and it runs ideally on every robot, or at least every robot that it was like kind of designed for. It was created in 2007 at the Stanford AI Lab, and now it's managed by the Open Source Robotics Foundation. You can see on the right, these are kind of the current supported versions. I think this one's a little bit out of date. The newest one is actually Noetic Ninja Beans, which we'll look at a little bit later. And then they have these cute little icons for that's kind of their mascot, I guess. So that's always fun. And we'll kind of get in a little bit more about like what these versions mean and what they're supported for a little bit later. But yeah, so ROS was born to help you kind of standardize your code. So ROS has two main sides to it, right? It has an operating system side and a user package side. So the operating system side is kind of what you would think of as ROS mainly. And it kind of does what an operating system, in the sense most of us know it actually does, right? It abstracts the hardware so you can use it easier, controls low-level devices, it implements commonly used functionality, message passing, and package management. All these things that you don't want to be doing. I mean, first of all, you don't want to be doing just because it's kind of a pain and it can really be standardized across your processes, but you don't want to be doing every time you make a new robot. And it makes it easier to kind of think about your robot in terms of more abstract, higher level features, right? You can, instead of saying, for example, okay, I need to move this clear path motor 60 degrees, you can just say, like, move the motor at this velocity. That's all you need to say. And when you give that to ROS, and if you have your system set up correctly, that's the kind of control you'll need to give instead of telling it exactly what. And then the second thing is a suite of user contributed packages. Now, this is, if you've ever used like Ubuntu, right, or a Linux package manager, this is kind of the same thing, right? Basically, you can download and freely use a whole bunch of packages for various robotics tasks. This is from SLAM, path planning, perception, vision, like item manipulation. All this is super easy to just download and implement right into your code, and it's there for you. It's all documented, and that's kind of the other very useful part of this, is that people are actually using ROS, and they're using it for the things that you probably want to be doing. And that means that you don't have to do it from scratch, which is often really nice, because doing a lot of this from scratch is pretty hard. We want to try to avoid that at least possible, right? That was one of the tenets behind this. Okay, so let's kind of talk about the features of ROS, and this is kind of the OS side. Here you can kind of see, if you kind of think of it as an analog to an OS, right? This is on top, you have navigation, task execution, simulation, perception, control, all these kind of things that almost mirror what an OS does, right? You have your web browser, window manager, email client. those are all things that you really need to be doing all the time on any computer. And your OS and programs in your OS provide a simple way to do that without having to yourself to code it every time. Okay, so now to get onto the philosophy of the OS side, right? There's kind of 4 main tenets, I'd say. Number 1 is peer-to-peer, right? So this means every piece of code is talking to each other, right? If you have, if you write something, you're going to be talking to someone else's tiny piece of code. And that's kind of, we'll get into a lot more later, but that's kind of the base level of how ROS work. Tools-based, right? So anytime you want to do something in particular, like log data, visualize data, really anything robotics-wise, there should be a tool you can download or smaller tools that you can do to do specifically that. And they should be really easy to incorporate into your already existing workflow. Thin, which just kind of makes sense, right? Ideally, we want our repositories and our robotics systems to be light, right? Not these huge pieces of software that are hundreds of gigabytes or whatever, but you only need exactly what you want, or you only have exactly what you want, and you don't need anything more, and make it as small as possible. This also encourages you to kind of, it should make it easier to create standalone packages. So having just less of a code base to get into makes it easier for you to understand more of what's going on and contribute yourself when that needs to happen. And then finally, multilingual, right? So this means ROS it's written in C++, but it is mostly language agnostic. If you want to use Python, C++, Lisp, Java, JavaScript to code your code that ROS runs, you can totally do that. Obviously, you need what's called a client library to be written, but for a lot of the popular languages already exist. And then the core guiding thing behind it is that it's free, open sourced, and community-based. So that's perfect for anyone who kind of just wants to get into robotics like us, students or researchers, because we want to be able to, number 1, get everything for free, and number 2, if we need to, dive into it and see how it's working and try and understand it at a deeper level. All right. So number 1 tool, if you're going to be using ROS ever, is the wiki, right? It has basically everything you'll need to know about ROS. If you ever get confused or you ever need to just look at something, this is where it's going to be. Even on here, the biggest one, I don't know if you guys can see my mouse. Can you?
Yes.
Okay, perfect. This packages one is like perfect, because essentially what that is that's all the documentation on all of the thousands of packages that exist in ROS. And that's going to be a big bulk of what you're using. Obviously, some of these tutorials are going to be useful for getting started, and maybe some robots or other things, but packages is at least where I personally spend a lot of my time, because that's really what I'm using in ROS. And there's a whole bunch of other stuff on here that would be cool to look through if you have time. Okay, and this is another link on the website. Like you can see, you can go to robots. This is a small subset of robots that are at least like by default supported in ROS. So, you can look on here and probably see stuff you've seen before. Roomba, at least, is one, maybe not as much as the others. Turtlebot is a pretty ubiquitous like testing robot. Maybe Lego NXT you might have played with. And this is, like I said, just a small subset. So there's good chances are if you're trying to buy a robot to do research on, or even just build one yourself and kind of using one of these as like a guide, good chances that support for your robot already exists with ROS. So there's packages that you can use that will just will handle all of the low-level hardware stuff for you, and you don't have to think about that as much, which is really nice. That's one of the good things about this. Obviously, that doesn't constrain you to using just these, right? If you build your own robots from scratch, that you can get that working in ROS too. Just a little bit more fiddling around with kind of details inside ROS, and a little bit more painful than just using one of these. Okay, so these are the main core concepts and the core things that the ROS offers, right? Nodes, message and topics, services, actions, ROS Master, parameters, and packages and stacks. And we'll go into each of them in detail. First up is nodes. So ROS nodes is kind of the most core piece of ROS. So these are single purpose executable programs. So that could be anything between, running a sensor, running a motor, building a map from sensor input path planning or creating a user interface, right? Any code that you write that does one single purpose, that's a node. They're individually compilable to execute and manage. So that means that they can be written in different languages and they're compiled separately, so there's no dependencies on each other's, and they're executed separately too. So that means if you write two nodes, they're totally separate from each other essentially. Nodes are written kind of like what I said before in a client library. The most two common ones and the ones that probably have the most documentation is ROS CPP, which is C++, and ROS Pi, which is Python. Those are the ones that I've definitely seen the most, although others exist. It just might be a little bit less documented, which is always not as fun. And the main thing behind nodes, right? Obviously, in isolation, a node doesn't really solve the problem that we were looking at. It's just a piece of code that can run. However, where it really gets powerful is that nodes can publish or subscribe to a topic, or they can also provide or use a service or action. And we'll get into what those mean later. But that kind of just means they can communicate to other nodes in certain ways. So first, and before we go forward, this is kind of some diagrams, example diagrams that I brought up. You can see each one of these on the left here, these blue boxes is a ROS node, and on the left here, or right here, the yellow kind of ovals, I guess. Polygons, no, not even polygons, shapes. Those are nodes as well. And you can kind of see, I think it's easier to see on the ref, like you might have a connect, right? That could be a single node, something that takes data from the connect and kind of makes an image from it or whatever you want to do. Or perhaps something that's driving the robot or driving the car here on the right could be a node, or maybe even a little bit less fine-grained than that, or more fine-grained, just running one of the motors or running the drivetrain on the car. And then we'll get into what the service and topic mean. Does anyone have any questions on this stuff so far? Okie dokie. All right. So first up, or next after this, the second, in my opinion, most important thing in ROS is a topic. Topics are named streams of messages with a defined type. So that kind of can sound kind of confusing at first, but this example might help, right? Data from a rangefinder, which is kind of just like a laser that spins around, that might be sent on a topic called scan, that will be the name of the topic, and the message has a type of laser scan. So what this means is that if we kind of go back to our pre-existing thing, right? This topic will accept messages from nodes of a certain data type. And maybe laser scan's a little bit too complicated. Let's look at this one on the bottom here, right? Let's say geometry messages / twist. And literally all that is it tells you a linear and of an angular velocity, right? If you've ever used JavaScript or JSON, they're basically just JSON objects. Objects is really what they are. They just contain certain structured data. So twist contains one 3D vector of a linear velocity and one 3D vector of an angular velocity. And what nodes can do is they can publish that twist message to this topic, right? So all these three nodes, let's pretend there's not a connect. Let's just pretend they are what we want them to be. Like maybe you have a path planner or something for one of these. Doesn't really matter. The topic is going to accept anything that's of type twist. And then these are our subscribers to it. So as soon as anything publishes to this topic, every subscriber is going to get that piece of data. So if we get from our path planner saying, okay, move at 5 meters per second in this direction and like an angular velocity of this direction, maybe it'll go to this node on the right, and that node will start telling the motors exactly how to move, so we actually get that velocity out of the robot. Does that make sense to everyone, that concept? Okay. So like I said, this publisher subscribe model, that's kind of what we're going to call it, publishing and subscribing, is what we'd say one-to-N broadcasting. Because if you have one node that publishes to this topic, it's going to hit all N subscribers, however many there are. If you have 100 nodes subscribing, they're all going to get that one piece of data. And like I said before, messages are just strictly typed data structures, and they are what's passed between nodes on this topic. Topics are really important. This is how you give data between nodes. And they're really useful because it means that all of your data for a certain purpose is going to be kind of funneled into this one topic. And let's say you wanted to read it out or change where it's going or change where it's coming from, you can do that without changing how the two nodes are talking to each other, right? So if I had, for example, I mean, the easiest way to think about it, no, oh, that's out of order. That's okay. The easiest way to think about it is like if you have, wait, I should have an example here. Oh, give me a second. I think my slideshow's out of order. Oh, yeah. 1 second. The point I'm trying to make, though, sorry for this mess up. Okay, there we go. Sorry for this. I don't know how I managed this one, but I did. Okay. Okay, awesome. Sorry about that. Okay, so this is the next thing I wanted to show. This is a lot of examples of what our thing might look like. So if we look at this one in the top left, right? So we have a node, a connect node. It publishes data from 3D data from the connect as messages to this 3D processing node, and there'd be some kind of topic in the middle. Maybe you'd call it like, I don't know, RGB image or something like that. And then the 3D processing node processes the connect data and says like, okay, maybe you have this object moving in this direction or something like that and sends it to the Arduino. But let's say we wanted to switch out our connect, right? We say, okay, let's use a different kind of 3D camera, right? Maybe like an Intel RealSense camera. All it means is that we don't have to change anything inside this 3D processing node. We don't even have to change the topic. We just have to switch in a different node that handles our RealSense camera and make sure that it's publishing the same data type to this topic. And as far as all the rest of our code knows, nothing changed. It's literally just the fact that we changed out a node and swapped it in. As long as it publishes the same thing, no one will know the wiser. And on the bottom, we have a little bit more complicated example, right? This looks like it's some kind of navigation. And then on the right, you have some kind of maybe path planner or something that's maybe deciding how something is moving. And you can just see each of these arrows, you have the name of a topic and then a certain message that's being published across it. You can kind of see, okay, this is how a bigger project might spread out all of their nodes and topics. Does that make sense to everyone? Any questions so far? Question. All right, perfect. And on the top right, I have some more example. I have another example of the message types, right? So I kind of said before that like, twist is two 3D vectors for linear and angular velocity, but the vector 3 is another message. So you can kind of nest different types of messages, and it goes down even further, right? The vector 3 is one float x64 for x, float 64 for y, and float 64 for z. And this is kind of like a basic data type. So if you've ever worked with JSON or anything similar, it's really just an object notation and way to serialize data really nicely. And if you receive a message, you always know what's going to be in it just because you know the data type, which is very nice. All right, so that's topics. Next up is services, right? So the big thing about topics that you might have seen is that the person who's subscribing to the topic never knows where their next message is coming. They'll know they're getting them because they're subscribed to the topic, but they have no way to know when it's coming, or if they need a message right now, they have no way to even request it, right? Because they're totally at the mercy of the publisher. The publisher is the only one who gets to decide when they send a message. So that's where ROS services come in, right? They're synchronous internode transactions, kind of just like topics, but they're blocking. So if you ask something, if you go to a service and ask something from it, you're going to wait for it, which is different from the topics in a sense, equally important, because sometimes you need maybe information only once, or you just need information right at this moment. And for both of those cases, the topic's not the perfect way because the topic kind of depends on timing. So unlike the one-to-one, one-to-n broadcast model of topics, the service is kind of a one-to-one request response model. So the requester sends some kind of message to the ROS, to the service, and then it provides it some amount of time later, and you're ensured that you're going to get some kind of response, assuming something didn't break. So some of the roles that a service might handle, right? Carry out remote computation, trigger some kind of functionality. So like maybe an initialization routine, right? Maybe you want to calibrate something in your robot. You can just send that request and it'll do it once. Or like a map server or static map, right? You can say, okay, I know you have this map. Can I get like the current one you're using right now? And here's kind of some examples of it here. Move base is essentially one of, we'll get into like what some of this is later. I don't think it's a good example, but essentially these are some real things that you might be seeing in actually doing stuff, right? All these are good examples. All the green things are actually nodes. And then some of the, I think this move base / action topics, that is the service they're talking about right now. So you can request certain things from those action topics and then it might do something for the robot. Okay. So we covered nodes, topics, and services. Those are the three main, so nodes are the main thing of ROS, and then services and topics are the main thing for communication between nodes. And those are what you're going to be dealing a lot with code. Now, ROS Master is kind of the way that ROS actually works, right? So every time you create a node or something similar, it needs to be also, okay, this is what I wanted to look at. So you need to almost register your node with something. In this case, it's called the master. So that number one, ROS knows that it's something that it needs to pay attention to. And then also you can begin subscribing and publishing to topics or services or requesting services that already exist. So this is how you kind of register and get all the information of your ROS environment. And the nice thing about this is, right, it's over TCP. And this might not seem like a big deal, the fact that these are over TCP. But what this means is that you can, number one, run multiple ROS masters, and they can communicate with each other if needed. Or you can have a node that's running on an entirely different machine that's just communicating over the network to different nodes. So the reason why this might be useful is, let's say you have some kind of robot that's navigating around an environment. And it's trying to do some image processing that is particularly computationally expensive. You might want to avoid doing that on the robot itself because you want to be able to avoid obstacles that it can see or do anything that like a mobile robot will want to do without slowing it down with this computation. So you can send that back to something maybe on some like beefier hardware, maybe in your lab, and it can do that image processing and send the result back to your robot. And you don't have to slow down what's going on in the robot in order to do that. And of course, you can also have stuff like multi-robot systems where you have robots communicating and all this kind of stuff. A lot of cool stuff you can do with this, the fact that this is over a network. So this is kind of one of the examples of like what ROS Master looks like. And this is both of these are very similar things to look at. So what you might be saying, for example, here, so this is our talker, and it's just a node. Like I said, both of these are just nodes. It's advertising that it has a topic called bar, right? And it's on some kind of IP port 1234. We don't have to worry about that. And then this listener, once it sends that to ROS Master and ROS Master registers that, okay, this talker is advertising this topic, then the listener can start subscribing to it and they can start sending messages back and forth to each other. And you can also see here on the bottom that they're sending, once they kind of connect to each other, they're actually sending messages back and forth to each other, right? They're not going through master all the time, which is good for like, it's peer-to-peer, which is kind of what we talked about in the beginning. Perfect. Well, okay, so that's ROS Master. Everything there makes sense. You're not going to be really dealing too much with ROS Master. It's just important to know that it exists and like, these nodes aren't just running in a vacuum, right? They have this thing that's controlling them. Perfect. All right. And now we're kind of getting further into this more like administrative part of ROS. So this isn't really code that you're going to be running, but things that kind of, when you start up a ROS instance, are going to come with it. And that one of those things is a parameter server, right? So what a parameter server is, it's a shared dictionary that's accessible inside ROS Master. And basically you can set certain parameters inside there for configuration or anything you want. So let's say that you have a node that starts up some kind of simulator, right? I don't know if you guys have ever used Gazebo. Just think of it as like a 3D simulator for robotics, right? And this is actually one of the use cases that I definitely use the parameter server for. By default, Gazebo kind of gives you the ability to launch a node that kind of opens up an empty world in Gazebo. But we don't really want to use an empty world all the time because there's a lot more interesting things to be looking at when you have obstacles. So what you can do is you can set a parameter in the parameter server that says, okay, tell Gazebo that when it starts up this file to use this world file. And then once you start that node, it'll look in the parameter server, say, okay, I should use this file and do that. And that's a simple example, but I hope you can kind of see how that might expand, right? If you want to change certain parameters about your robot, right? Or maybe you have some path planner that you kind of want to subtly tweak certain things about. You can all do that from within the parameter server instead of having to go into your code and playing with each of these values every time. It allows you to easily kind of centralize all of the configuration settings you have for your entire project, which is really nice. Okay. The other thing with like administration is ROS bags. These are very important if you're ever going to be doing anything with like testing. This is how you data log in ROS. So what a ROS bag essentially is, it's like a pseudo node almost. And all it does is it subscribes to a ROS topic and it collects and logs every single message that is received on that topic. And then what you can do to it, number one, you could read it out, right? So if you just wanted to check some log data, you could go through it. But the real important thing is you can play it back into ROS. So for example, let's say you have a camera, right? Let's say you have a camera and a LiDAR. And then maybe even some odometry values, which is tells you how the robot moved from like GPS and a gyroscope. So you run your robot in the real world test and you get all these data values, right? You have your camera running, you have your LiDAR running the scanning things, and you have your LiDAR that's actually picking up, or you have your gyroscope that's actually picking up values and kind of tracking where you are. So you run this real world test and something goes wrong, let's say, and you want to go back and fix it. Now, it can be really expensive to try and run these real world tests over and over and over again. So what you can do is you can bag all the data from the LiDAR topic, the camera topic, and the odometry topic, and just play it back into your ROS node. Because the rest of your code doesn't know if it's getting data from a real life source or if it's being sent in it from a bag or a simulation. So what it allows you to do is simulate the test you just ran without having to actually dedicate the physical resources to running it, which is really useful for testing. And then obviously you can save them. You can even send them to other people. So maybe if you have like a good camera image that you want to run something on, you can maybe send it to someone else's robot and run that same simulation on, which is really cool. Alrighty, that's ROS bags. Okay, so that's, if we kind of go back, that's all of the base things about ROS itself, right? Those are all the components that you have to be worried about in the central part of ROS. And now I kind of want to talk about how we use ROS, what tools we use, and kind of as a developer, what we're going to be looking for when we start using it. So first of all, ROS is currently supported only on Ubuntu and Debian, which are two Linux platforms. There are variants on Windows and Mac OS, but they're experimental. And unless you like solving obscure problems that probably don't have documentation, you probably don't want to be worried with dealing with those. The most current one, the most up-to-date is Noetic Ninjames. That's for Ubuntu 20.04. I think there's one for 21.04, but 20.4 is kind of the recommended one. So that's the one I would recommend looking at. There's also ROS 2, which is kind of incorporating a lot of the changes that have come out of ROS in the past, I don't know how many, 14 years since it came out. But again, both are going to be supported right now, and ROS 2 is not as well documented. So if you're trying to learn this stuff and you're kind of at like a research perspective or just like a student, I would stick with ROS 1 for now, right? They have plans to support both at once, and it seems like ROS 2 is still in active development. So stick with ROS 1 is my suggestion for now. Obviously, if you're interested, you can kind of see what's different between them. It's not too much, but there are some noteworthy changes and obviously problems that you could run into that don't have easy solutions. Okay, so like I said, ROS is on Linux, right? So that means you're going to be using a lot of Linux tools. If you're not familiar with the command line before you use ROS, I definitely recommend getting familiar with it. There's just a lot of Linux commands and then ROS versions of those Linux commands that will really only make sense if you're familiar with using Linux. And that shouldn't take too long, I don't think. Just kind of, if you have a chance, maybe open a Linux shell and start trying to do things that you might want to do in Windows, like opening files, moving things, copying things. And after doing that for a little bit, I think you should be pretty up to speed for what this is doing. So that's what that entire suite of things is called, where you run ROS tools, and the command line is called ROS Bash. Has a whole bunch of utilities on the command line. And in order to use that, and I know personally this is something that like frustrated me, you kind of have to run this command where you're sourcing some file that ROS sets up, and it essentially initializes all these commands and allows you to use them. And you got to do that every time you use ROS in the command line. And there's an easier way to do it. You can add it to your like setup file for your shell, but just remember that if something's not going wrong and ROS is telling you that, or ROS is telling you like packages don't exist or certain things, that might be the problem. And I guess now we should talk about packages, right? So software in ROS kind of at the lowest level is organized into packages. So if you've ever used number one, I think Python might be a good example, right? If you ever use like pip. ROS packages are similar in a lot of, very similar to like pip packages, for example. It's basically a collection of nodes, messages, and services that all do one like combined purpose, right? It serves one specific purpose, and it provides a ROS interface to allow you to use ROS to interplay with all of those purposes. So for example, you might have a SLAM node that literally only does SLAM, right? It takes in some amount of like sensor data and generates a map of your environment as you move around it. And that's all the node does. You might have a node for path planning, or a node for making your camera work, or a node for controlling your motors, or a package for controlling your motors, sorry. Because nodes do very specific things. Like a node might be controlling one motor, or maybe even just taking some kind of motor input and sending it to the hardware. A package will kind of encapsulate those nodes and a little bit higher level than that. And this is kind of the ROS system for how it works. You might see these terms a lot, right? So a stack is a collection of packages. One of the stacks that I'm super familiar with is the navigation stack. So that's all of these packages that would help you navigate a robot. So path planning, SLAM, all these different kinds of things that might help you move a robot around autonomously or teleop-wise. A repository is an even bigger collection. It might have multiple stacks. And I think that would be like a full robot almost. So if you want to use ROS to control your, I don't know, like Baxter robot, which is like a two-handed robot, you might make a whole repository for controlling various subsystems, right? It has two arms, or maybe you might have a stack for like sensor, processing all the sensor data and giving it to the arms for path planning, stuff like that. And you might have multiple stacks for doing stuff in there. And then on the highest level is basically everything in ROS, the ROS universe. So that's going to be people's repositories that have stacks that have packages in them. All right, I think we're good there. So packages, kind of like we said, they're the most atomic unit for a build. They contain all of the source files for multiple nodes and doing everything. And if you've ever worked with like C++, you'll probably be familiar with the concept, but ROS has its own custom build tool called Catkin. What it does is it looks through all of your packages and it figures out how to build them. It's basically just, I think, CMake augmented with some Python if you're curious, but it's specific for ROS. So if you have a whole bunch of packages, there's kind of two steps to it. You download the packages, add your code into it if you need it, and then you can do this Catkin build that'll build them all and turn them all into executable files or whatever format that you're using. Like Python obviously isn't executable, it's interpreted, but for example, C++, you need to turn it into an executable file. So it'll figure all that out and do it. And if you have other languages in there, it'll figure that out too and put it into one runnable package for you, which is really nice. And if you haven't used C++ or something like it, you might be a little intimidated by some of the terms and the environments there, but getting familiar with it and maybe even looking at a basic, like looking up what CMake is and kind of seeing what it's doing might give you a better idea of what Catkin is doing, because it's really just that with a little bit more functionality. And a Catkin workspace is essentially just your project space. That's where all of your code, everything you're working on is going to be. And here's a little bit of an example of what that might look like. You kind of have your workspace folder, and then you have these like 4 different main folders. You have your source. That's where all of the source code goes. So everything you write, everything you download that you want to run, all like the raw code that you can actually read as a human. Build space is where CMake and Catkin kind of does their various things to build the files, and intermediate things go there. Development is where the built targets, so this is once they're done, they're just not installed yet. This is where it goes. And then the install space is where you actually install these finished and built packages, and they're ready to be used at that point. So there's a ton of stuff you can do here. And I think even like I'm not super familiar with it, because if we're working on small projects, generally you'll just have a bunch of files in your source. You'll build those files and then you should be able to use them after that. But for larger projects, you might have to dig a little bit deeper into this stuff and get more familiar with it. But that, as you know, some beginners, this isn't super important. And yeah, that's kind of the general overview of ROS. There's a lot, obviously we covered a lot of things. If you guys have any questions, please feel free. The biggest thing that I would recommend, right? Obviously I can talk at you for a while and tell you, okay, these are the core concepts, but you really need to use this stuff. And luckily there's a lot of good tutorials. TurtleSim is kind of like a built-in tutorial on how to use ROS. It kind of comes with this little GUI, and you can learn how to control this turtle through like autonomous or user controlled. And there's a lot of walkthroughs on getting this stuff running. And because of how it works, you're going to have to become familiar with a lot of the tools that I've been talking about this whole time in order to get some of this running and working. On the other hand, if you kind of want to dive into something more application-based, you can use a simulator like Gazebo to do really anything. A good tutorial. I actually last semester for this club, I kind of gave a little talk on using Gazebo to navigate a robot around a space, and that involved a lot of the things we were doing. So if you wanted to get a little bit more hands-on in this space, that might be a good place to start. And if you just Google like ROS tutorials on doing certain things, maybe like navigation or something like that, it'll give you a guide through, probably in simulation, on whatever you want, which is really cool. And yeah, that was kind of what I wanted to talk about with ROS. Does anyone have any questions or comments, concerns about what we talked about?
Hey, Jack.
Hi, Jack.
I came in a little late, so I was curious. This seems like mainly a hardware communication language or framework, right? How easy is it to integrate that into other, just other programs or packages in general, in terms of like machine learning, for instance? Yeah, what do you think?
Yeah, so I don't know if it's exactly hardware. Like if you can make a ROS node that communicates with hardware, but really it's just for having communication between any two pieces of code being standardized. And
Right.
because these pieces of code are written in Python or C++, you can use any existing pieces of code, libraries, anything you want in that
Yeah.
node. So
So
if
you
you
just
wanted,
plug this into whatever you really need to.
yeah,
Okay, cool.
it's really more you're plugging whatever you need into ROS, because ROS is kind of just that modular. It really allows anything you want to do.
Okay, I'm sorry. Did you say that this is written in C++ or Python?
ROS, I think like at the core is written in C++, but there's a bunch of different client languages. So you can write ROS nodes in C++. I think I had a list somewhere, C++, Python,
Oh,
Java,
okay.
JavaScript. So anything you really want.
Cool. Yeah, I thought it was sort of more its own descriptive language.
No. The only thing that's really descriptive for ROS is communicating between two nodes, right? Everything in the code, you can do whatever you want.
Nice.
And so, yeah, if you had a camera and you were reading in some information, once you get that camera data, you're free to do with whatever the hell you want with it, whether that be some kind of classical CV algorithm or machine learning, right? Do whatever you want. Message in the chat. Would you recommend ROS? So Stephen Smith says, would you recommend ROS for situations that require real-time responses? Yeah, absolutely, right? So obviously it's going to be introducing some amount of latency because you have this ROS master. But I can say without hesitation that it has been used in places that require real-time responses, right? Maybe not on the scale of like autonomous driving, right? Very high speed stuff, but for things that just are actually doing things in the real world, real time, ROSs definitely have been used and is useful for that thing, for that kind of stuff. Does that make sense? Does that answer your question? Perfect. And yeah, another thing that I want to stress, right? ROS is a solution to this problem of kind of like a software middleware that handles communication. It's not the solution. It's nice for us because it's open source and free, but plenty of companies have written their own proprietary solutions, and I believe there are also some other like competitors in the space. ROS is kind of just the big one right now, and there's a lot of documentation for it. It's pretty easy to get into, so a good starting place. It was pretty interesting. I know some of you were there, but like recently, like Nokia Bell Labs kind of gave a talk on this high level language almost for doing this kind of thing. They wrote their own middleware, and you can kind of just like write in their own interpreted language, like, hey, tell this robot to go to here at this time and do this task. So that's another implementation of this idea. I think they even, I don't know if it was them who said it or someone I was talking to, but like that's almost a different form of ROS, and that seemed really interesting. Yeah, Jack put it in the chat, resh.io/play. But the point of ROS is not to be restrictive, right? It's to let you do what you want to do. Unfortunately, as you get into it, I think they accomplish that with some amount of success, but it can be kind of frustrating with some of the limitations and that topics provide. But that's kind of once you get down to the dirty. On the base level, you can really do whatever you want with it. Well, if there are no more questions, I think we're probably good to head out earlier. If you want to talk to me after, I'll probably stay around for a little bit. But thanks everyone for coming. Really appreciate it. Hope you learned something and go out and play with this stuff.